Okay, so last year we did 3 main units. We talked about a lot of algebra, and yesterday my goal was to review some algebra skills, and hopefully that kind of brought back some good times from last year. Maybe not. But at least you recall the concepts of like how to factor, how to expand, how to isolate and get x by itself. Because those are skills that we'll use as we go along. We're probably not going to be like specifically, like I don't think I'll be teaching like those individual skills of factoring and foiling and solving, but like we will use them as we go through. Does that make sense? The second unit we did was all about functions. And so that's where we're going to kind of pick up in grade 12. We're now going to extrapolate to new types of functions. And so I want to remind you guys of an analogy that I often use with functions. It's the idea of a machine. Do you guys remember talking about this at all last year, the idea of like a function machine? So I love the analogy of like, say, a vending machine, because in my mind I can think of a function like a vending machine. So how does a vending machine work? Well, I go to the vending machine and I put in money. I input something, and then what does the vending machine do? It gives me back something. Does that make sense? Now, I mean, maybe you got to tweak the vending machine in your mind a little bit, because I'd say most vending machines you put in like what, $1 or $1.25. Like everything is $1.25. So maybe kind of tweak it in your mind and think of a vending machine that, you know, there's an item in the vending machine for $1. There's an item in the vending machine for $2. There's also an item in the vending machine for $3. And technically, if we're talking math-wise, there should also be an item in the vending machine for $1.01, and $1.02, and $1.03. And maybe even there should be items for $1.000001. And if you get where I'm going with this analogy, we should be able to input basically any value you want. So what's the input value in math? X, yeah. The input value is X. So in this example I screen captured from somewhere here, this is your vending machine equation. Your vending machine equation means that if you put in X, what this vending machine will do is it will double X and then add 3. So if I had to put this into words, this equation, this function, functions are equations basically, right? Means take any number, I don't know what that number is yet, but take any number, double it, and add 3. Okay. Now, you notice I use those words though, like any number. That's the problem. We don't know what we're inputting, right? So that's why we often have to define the input. And so like up here, I told you that X was 4. So then you say, oh, okay, well, double 4, so 2 times 4 is 8, plus 3 is 4. Often what you're going to be asked to do then, often you're going to be asked to try to figure out what the output is based on a known input, or you're going to be given an output and asked to work backwards and find the input. Does that make sense? Okay, grab your graphing calculators. I hope you have them, because I want to do some just a basic reminding of how to do things. And I guess if you don't have one, then just watch, I guess. Get a graphing calculator. Is it like nearby?
Not here. But
that doesn't help then. Okay. Okay. So last year we talked about 2 main types of functions. We talked about linear functions and we talked about quadratic functions. So let's just type in a generic linear function. How about we go with take any number and add 3. That's what this means. Take a number, add 3. We don't know what that number is. And so then the question is, well, what would this look like in a graphical form? And before you even press graph, like Sean's already showing with his hands, right? You guys should know it's a nice straight line, right? Okay, a couple of calculator skills then that you guys need to recall. Depends on who and what last you did with your calculator, but you might want to change the window size. My window size is currently going from -10 to +10 with a scale factor of 1 and -10 to +10 with a scale factor of 1. I mean, you can mess around with this. And you're probably going to need to, depending on what our function looks like, but something like this should probably work for our basic functions. Okay. Or you can always go like zoom, and then if you go down to the 6th one, zoom standard. That will give you a nice window, basically, right? But mess around with it as you need to. Is that familiar? Okay. So what this function basically implies is take any number and add 3. So there are a couple of tools you can use to calculate certain things that are useful to you. So hopefully you recall this. If you go second, calculate, there's a whole bunch of things in here that we can actually use. Value, 0, min, max, and intersect. Does that sound familiar? So let's talk about the first one. Value is kind of like, if you like my vending machine analogy, it would be like, okay, well, what if I have $1? what would this vending machine give me back? So if I input 1 into my equation, I get 4. Because this particular vending machine, okay, my analogies are going to break down a little bit, but this particular vending machine basically says if you put in $1, it's going to add 3 to it and give you back 4. Does that make sense? Whereas if you were to put in $500, how much would you get back? 503. Okay, why didn't this work? Say that louder. Yeah, so back to window size, right? So make sure your window size is capable of going that high, right? So our window only lets your X inputs go as high as 10, so maybe I should make it go as high as 504. Okay, this is really going to script my graph now, because what's really happened is the graph is going really far over there, and this only gets as high as 10 right here. I'm expecting the answer to be 500 and something, so maybe I'll go to 550 or something like that. No. Now maybe the graph will look better, right? So again, second calculate. Whoops, I'll get to that one in a second. Second calculate a value. If you input 500, let's not go 5,000, then it gives you back 503. Does this make sense? Okay, cool. Okay, other skills that you can use in terms of solving is you could go to that table I just kind of played with there. And basically it'll tell you inputs and outputs right next to each other the whole way through. Like you probably can recognize they all differ in this example by 3. Still good? Okay. Other nifty tricks you can play then. Let's say that you wanted to get all the way up to 500 and you didn't want to press this down button for like the next 2 minutes. You guys recall a fast way of getting there? You guys remember me telling you? Did I tell you? I don't even remember whether I did. Okay, there's a way that you can set your table. So, I mean, literally it's right up here above window. It says table set. You guess that, right? So, second table set. And so there's a couple of things you can mess around with here. First one is table start. It's probably up to 16 now because that's about how far it got when I was just pressing down randomly. So, I mean, let's start it at 500. That makes sense. And now if I go to my table, it should auto start at 500 for me. So it's kind of like that value option if you want to figure out what it'll look like. I mean, it only works from the input point of view. Another nifty thing you can do is you can make your table go up by not by 1s, but make it go up by a different value. So for example, let's say I want it to go up by 10s. Now it'll give me 500, 510, 520, 530. Do all of the numbers in between, do they still exist? Sure, exactly. Yeah, they do. It's just we're not recording them in this particular table of values. So if you like my vending machine analogy, again, it's like you can input $1 or $2 or $3, but technically you should be able to input $1.23. I mean, in a real life vending machine, you wouldn't. Does that work? Okay. Other things that are useful. Second, calculate 0. Do you guys remember what 0 does? Yeah, this isn't going to look very nice. I'm just going to go back to regular zoom. There we go. What does a 0 calculate? Yes, it calculates the intercept, but we got to be specific which type of intercept, the x or the y. X-intercept. Okay, so if you're looking at the graph right here, it's actually currently on my y-intercept of 3. A y-intercept occurs when x is 0. And so if x is 0, 0 plus 3 would give you 3. So we're currently on the y-intercept. I think that was just random luck. The x-intercept is right over here. So the way this particular function works then is you want to go on the left-hand side, over here, press enter. Go on the right-hand side, press enter. And like these little arrows kind of narrow down like a search radius, basically. Because otherwise your calculator, as a computer, has way too much area to search. Because otherwise you're literally asking it to search from negative infinity to positive infinity.
That's a lot.
It's undefinable, right? Not only is it that's a lot, that's an impossible thing for your calculator to do because it's going from a number that doesn't exist because I mean, you can always go lower than the number, right? Like, think of the smallest, the lowest number you can think of. Negative a billion. Then it can go to negative a billion and 1. Then negative a billion and 2. Does that make sense? Anyways. And don't forget to press enter one more time. Grab the door. It's not your job. So this one's actually negative 3. So what this one does is it kind of figures out if you want your output to become 0, this will tell you what the input would need to be to get there. That work? Awesome. Okay. What else do we got here? Maximums and minimums really only work if you have graphs that have maximums and minimums. And linear graphs, what we started with so far, they don't really have those. So we're very, very quickly going to start learning new functions. And the only other function we've really talked about is a quadratic. So why don't I do a basic quadratic function? Here, x squared minus 4. So before I press graph, what's it going to look like? Parabola facing upwards. Why upwards? Because it has a positive number in front of the largest term. We call it a leading coefficient. If I had thrown like a -2 right here, what that would do is it would make the graph upside down, and that 2 kind of makes it steeper. You guys recall that? So I think I just want the normal graph though. So now we've got a graph like such, and now I could actually calculate a minimum if I really wanted to. Second, calculate minimum. Okay, now if you have more than one graph, you do have to flip between graphs. And so it's currently on the linear graph. So to get it to the quadratic graph, just press down and it'll flip between graphs. And then this works kind of the exact same way as the last one. Go on the left-hand side of where you know that minimum value is. Go on the right-hand side of where that minimum value is. How far on either side, it really doesn't matter, just so long as it's on either side. And one more time, and there's our minimum value. It's a good teachable moment here too. So our minimum value is -1.84 e -6 y equals -4. This number is essentially 0. As to why this works this way, I don't really have a great answer, except keep in mind this is your calculator as a machine trying to do some sort of like calculation to try to solve where that lowest point is there. And for whatever reason, it decided to call this number, how would we write that? 0.00000184. That makes sense. Essentially, that number is 0. Does that make sense? I don't know why calculators do that. Does that work? Okay, and last skill, and I'll move on here. You can also intersect. In order to intersect, though, you do need 2 graphs, at least, right? And so, honestly, you don't really need to put the cursor exactly over top, but it just needs to be in the generic area. And really, you're just pressing enter 3 times, and this will tell you where they cross. This, by the way, is an answer to a system of equations. Remember how we did that yesterday with a substitution? So if you have the equations, you can just plug them in your calculator and system of equations and solve. Sometimes it's a nice even value. The third spot is just you have to press enter, so it doesn't have to go anywhere. If you want to redo it again and find like the other intersection point, you just got to move your cursor closer to that intersection. So like over here, and then one more time. Anyways, is that familiar? Okay, cool. So those are skills that we're going to work on today. Only the new twist now is we're not going to be working with just linear and quadratic graphs. Pretty much the bulk of the first half of the year for math, pretty much everything that is not on, you know that data sheet I gave you here? The first half of the year is going to be talking about graphs. And so all of these equations we really don't use. We'll use this in the second half of the year once we're past all these graphs. But basically for the next month and a half, really our process is going to look very similar most of the time. I'm going to introduce some new concepts about how graphs work. They're not going to be straight lines or quadratics all the time. We're going to add some new stuff to it. We're going to talk about properties of those graphs. We're going to talk about how to solve those graphs. We're going to talk about where they might be applicable in everyday life scenarios. And that's kind of where we're going. Sound good? Okay. So let me go through some notes then. So we talked about functions. So long as you guys basically get the concept of inputs and outputs as to how a function works, you're good. Sometimes rather than writing x's and y's, sometimes we write y as f bracket x. Have I shown you guys this notation before? Yeah, it basically refers to that x gets plugged into the function. And when you do that, as a function, it gives you back an output. So I'm going to use that vending machine analogy a lot. You may have also heard this term before, the vertical line test. If you can see a graph, so long as like you have a vertical line, let me just make a line here, and it only ever touches once, it's a function. Sometimes maybe a better way of using that is to talk about what's not a function. let's say you have a graph here, and your function looks like this. Sine actually will work, but if you flip them, sometimes they won't. But like logs will actually also work too. Like everything that we're going to talk about is going to be a function. So this one here then does not pass that function test because, like right here, let's say I asked you to input 0. How many answers would you get if you input 0? Yeah, like +7, +2, and -3. And that becomes kind of a problem. Now, this would be a really cool vending machine. If you put in $1 and you got back a bag of chips, a pop, and a chocolate bar, vending machine kind of busted. Does that make sense?
Not for us.
Not for you, obviously, right? But like I said, if that analogy makes sense, a function is really supposed to be you put in $1, you get back 1 chocolate bar. Right? If you're getting back more than one thing, then it's no longer a function. I should make sure I'm clear. It is possible to get back the same answer more than once. It's okay for you to say, like, let's say you put in $2 right here. If you put in $2, you'd get 4. Or if you put in -$2, you'd also get 4. That's still valid. It's okay to get the same output multiple ways, but it's not okay for you to plug in one number and get back 4 answers. Does that work? Hopefully. Okay, just more stuff that we've just talked about for the last little while. Inputs and outputs. Terms we have to go along with those. I think you guys know these words, domain and range. Remember, we talked about that last year, right? Domain basically refers to what valid x numbers are there, and range refers to what valid y numbers are there. Well, why don't I start with these first 2 graphs, because the first 2 you guys recognize. Right? Here's a linear graph. What sort of input numbers can you use? And the answer is, well, actually you can use anything you want. You want to input -2? That would be right about, well, I guess if that's -1, that's -2 would be right here. You input -2. Could you input -17? Can you see it on your graph? But can you still input it if you just made the graph bigger? Sure. What about for outputs? Could you have any output value you wanted? The answer is yeah. I mean, pretty much this graph will go either way. So there's a couple of ways that we would write that. Sometimes we write it like this. X is an element of the reals. You guys recall that notation? And we might say that like y is an element of the reals. Basically meaning that you can have any x value, any y value you want. They're all permissible. That's not always the case for every function. For example, this next quadratic one here, for domain, you can plug in any x value you want.
All high school students, can you please proceed to the gym? All high school students, please proceed to the gym.
What's my range though? Do you guys recall this from last year? Yes, we would write it like this. Y is greater than or equal to -4. And the reason for that is -4 seems to be as low as this graph goes. I can't get numbers down here at -5 or -6 or -7. There is no such way of doing that. So if you like my vending machine analogy, if I plug in $1 or I plug in $2 or I plug in $9, it does not matter. This vending machine is not capable of spitting out a car. Does that make sense? It's capable of giving me a chocolate bar. It's capable of giving me a chips. But like, it just, the output does not go that low. Does that make sense? Okay, cool. Let's head down to the gym. We'll pick it up whenever this thing is done, I guess. Pause it. Okay. Where were we when we left off? Oh, right, talking about the quadratic graph and domain and range. Okay. So, did everybody understand how I wrote the x is greater than or equal to -4 concept?
Yeah.
Is this review, like, should I be going a little faster then?
Yeah.
Okay, we'll move on. Our goal now then, start talking about different types of graphs. And I've been hinting at this for like the last day and a half. So, one thing I want to point out then is that this graph right here, straight line, how many maximum or minimum points does it have? Let's say it doesn't have any, it has 0. Well, this is a quadratic graph. How many different like maximum minimum points does it have? Well, it has 1. It has 1 minimum, right? Well, this is a cubic graph. We call anything to the power of 3 cubic. And the reason I can tell that is because it, rather than being like a single quadratic, it's like a quadratic merged into a second quadratic, and it has 2 of these points. Does that make sense? And so actually there's like a pattern that will continue going on as the degree Do you guys know that word degree? We talked about that before. Degree is this number right here. 1 doesn't write the 1, but 1 is the exponent. This is a degree of 2, and this is a degree of 3. Have you heard that before? So as we start getting into higher and higher exponents, the graphs become more complex. Basically, they start having more maximums and minimums. One of the things we can do is we can write a graph in factored form. And that's what we learned to do a little bit last year, because we recognize that these points right here are very important as zeros. And then another thing we learned about last year was about leading coefficients, which controls whether the graph is right side up or upside down. What is the nature of the leading coefficient for this graph? Positive or negative?
Negative.
Good. Okay. So here's my challenge then. Our goal then is to try to write an equation for the graph we just saw on the previous slide. I'm going to walk you through this one here because I don't think we've really done something quite like this before. So our goal is to write it in factored form than in standard form. So factored form usually looks something like this. Y equals A x minus B x minus C. I'm going to fill in some numbers later, but that's kind of how we write something in a factored form. So let's start with those two factors. What are these factors based on? How can I tell them? You guys remember?
Isn't it like 2 points on the graph? Or no?
And it's these 2 points. It's based on your x-intercepts. Okay. So let's do this one right here. If one of the roots, if one of the x-intercepts is 4, then the factor has to be x minus 4. Does that make sense? Because if you plug in 4, 4 minus 4 will give you 0. One of the terms I'm going to use a lot over the next couple of days is factor and root. Maybe let's write this down somewhere here. The factor is x minus 4 because you can either call it a root or you can call it an x-intercept, whatever you want to call it there, is 4. They're like opposites of each other. If the factor is x minus 4, the root is 4. Does that make sense? What's the other root then? Okay, so this one's kind of odd, but I mean, you'd actually do the exact same thing. You go x minus 0. That'd be exciting. X minus 0, that's kind of pointless, isn't it? So often we just kind of skip the minus 0 and just go next to an x. That is the start of our quadratic. Now, if I were to try to put that in my graphing calculator, though, just to kind of check and make sure that I'm doing it right, it would be like x and x minus 4. That's a good way of drawing it. Does this quadratic here look like the one that was just on the other slide there? No. There's a couple of problems. I mean, it's a quadratic, but I mean, it's facing the wrong way. So one other thing I haven't done yet is I haven't dealt with this leading coefficient value. What do I know about this leading coefficient value? For sure it has to be negative. But is it -1? Is it -2? Is it -3? Is it -9/7? We don't actually know what that value is. So it's going to be our job to try to find that value. So the way we solve this then is we write it something like this. Y equals A. We still don't know that number. And then we write x minus 4 and x. And what we're going to do is we're going to solve for A. So this is why we were working on algebra yesterday.
Do you plug in a number for y?
We plug in a number for y and for x. Did we do some of this last year? Solving for the A value? Here's the thing. We need to know an xy pair.
Oh, that's the...
Now, that's why I gave you this point right here. We don't want to use the x-intercepts again. We've already used them once before. So we don't want to use them again, but that's why I give you this point 2, too. So we know that we can plug in, let's see if I can get a full page going again here. We can plug in 2 for x and for y, I guess. So A, 2 minus 4, 2. We did do this last year, didn't we? Should ring some bells. And now it's our job to solve for A. Before I even get my answer and solve for it, if it's not negative, something's screwed up. Does that make sense? Because I know for sure it should be negative because the graph's upside down. So 2 minus 4 is -2, right here, times by 2. That number there is like -4, right? So what we really have is like negative 4a equals 2. Divide by negative 4, divide by negative 4. If I reduce it, it's a half. You guys able to follow that? So good news, it's negative. But the other issue is we had to know what the actual value of the coefficient is. It's not always negative 1. Sometimes it's negative a half, negative 2, negative 5 over 17. I don't know which number. So we finally have our full factored form coefficient. So in our factored form, the equation is y equals negative 1/2. And then it was, why don't I write it like this, x and x minus 4. Sense? What does this information tell us? It tells us, and probably three main things. It tells us the shape of the graph. It's upside down, the negative. It tells us we have a root at 0. And it tells us we have a root at 4. And all of those things fit what our graph showed. The other thing I asked you to do was write it in standard form. Do you guys recall that terminology? Yeah, kind of something along those lines. So, long story short, expand it. Like, don't have it in brackets anymore, but have everything get, like, foiled out, if you like that terminology. So, if you're done with that, it should hopefully look like 1/2 x squared plus 2x, I think is what it should be. Because you're going to do x times x right here to get x squared, and then also times it by negative 1/2. And then you're going to do x times negative 4, which would be negative 4x. But then you have to times it by negative 1/2, so the double negative makes it positive, and 1/2 of 4 is 2. What's our y-intercept based on this standard form? Sometimes we write it as like an x squared and then an x, and then we write a number afterwards. Yeah. We could write the plus 0 if we really wanted to. So that means our y-intercept, if you guys recall from last year, this value right here implies our y-intercept is 0. Because there isn't a number there, right? And if I go back to my graph, the y-intercept is indeed 0. Right, you can come back to her. Does that make sense? Something that like you guys recall a little bit of doing? Awesome. Okay. Okay, so let's talk then about our goal for the unit. We're going to talk about polynomial functions. Okay, the same sort of principles that we did with linears and quadratics are going to apply going forward. You can write a polynomial so long as you can write it like this: a leading coefficient with x to some power. I don't know how high that power is. That power could be 5, 4, 3, 1. I don't know. If it's to the power of 1, it's linear. If it's to the power of 2, it's quadratic. Now we're going to open things up to any number here. What then happens is then we're going to drop the exponent by 1. So if it used to be an x to the 4, this will now be x to the 3. And then this would be x to the 2. And this would be x to the 1. Does that make sense? Like that's what this notation here means, is whatever this exponent is, this one's 1 less, this one's 2 less, this is 3 less. So this is an example of a polynomial. It's quadratic, but it's a polynomial. This is a polynomial too. Same thing with this one. Does this one have a, or either of these two have like a last number? Well, I guess it has a plus 0, but that's still fine. That's valid. Does that work? Now this one is the craziest one of all. Doesn't poly kind of imply more than 1? You look at that and you go, how in the world can that be polynomial? But it is. Because really what you have are like 0 x to the 5s, and you have 0 x to the 4s, and you have 0 x to the 3s. You get where I'm going here? All the way down to 0 x to the 1s, and then you have 5. Does that make sense? So I know it seems weird that this thing right here could be considered polynomial, but it actually is. We don't write all those zeros everywhere. So I think I have one of these ones. No, I have them in order here. Linear means you have an x to the 1. Quadratic is an x squared. Cubic is x3. Quartic is x4. And quintic is x5. And generally, we don't go much higher than about 5 or 6. But I mean, if you get the idea behind this, I guess you could, but that's just ridiculous. Does that work? What about x to the 0? Is that possible? That's actually what this is right here. This is 5 x to the 0s. Does anyone remember what x to the 0 actually means? Does anyone know what an exponent of 0 means? It means 1, yeah. If you want to test it in your calculator here, anything to the 0 means 1. Like if I were to go, come on, calculator. If I were going to go 8 to the 0, well, that should still work. It's because it's times by 9. That's not going to work. 8 to the 0 is 1. 89 to the 0 is 1. So if you guys don't remember that rule, that's hopefully one you can now remember going forward. This is really 5 times x to the 0, so it's really 5 times 1. So anything that's just literally a coefficient is actually, it actually has an x value. But that x value is x to the 0. So the rest of the notes here, if I remember correctly, we're now just going to look at some graphs and some properties here. So here's a linear. Here's a quadratic. See how it has, like, say, 1? Sometimes I call it a turning point. Because see how it kind of turns around? It's almost like this is a linear graph, and that's a linear graph, and it's turned around on itself. So, like this graph right here, see how it turns around 1, 2, 3, 4, 5 times? That means this is probably an x to the 6 graph. And see how this one turns around 1, 2, 3, 4 times? It's an x to the 5 graph. And this one turns around 1, 2, 3 times. It's an x to the 4 graph. This one turns around twice. It's an x to the 3. That's an x squared. That's an x to the 1.
Why is it always one more?
Because I'm just choosing to go up by 1, basically. I'm just trying to show you all the possibilities. Because, I mean, you can make it x to the 47, I guess. All right? But what I'm trying to say here is that we're going to cover basically from x to the 0 graphs all the way up to x to the, usually 5 or 6 is usually how far we'll go. So, I just pulled this slide out to remind you of some terminology. This term right here in front of the x squared is called the leading coefficient. It determines whether the graph kind of goes upside down or not. The actual largest coefficient, the largest exponent is called a degree. This would be kind of known as a linear term. This would be known as a constant term. If I want to throw one more thing in here, the constant term is actually the y-intercept. I think you guys knew that already. Okay, you guys remember talking about quadratics and how, like, on a quadratic, the graph, if it crosses twice, then there's 2 answers. If the graph crosses once, there could be 1 answer, and then there's also the possibility that the graph doesn't cross at all. Well, that same sort of logic applies not only to quadratics, but also to higher degree polynomials as we go through these graphs. And so what I'd like to do here is talk about how many x-intercepts or roots a function can have. So I'm going to start at the bottom. Constant functions. Okay. This is a graph like y equals 2. Is there a variable in this graph? I guess if you did that, you could say, yeah, there is. You have x 0 times. I guess you could say maybe there isn't a variable in this graph. If you want to use the vending machine analogy, this would be like if you put in $1, you get back 2. If you put in $5, you get back 2. If you put in $100, you get back 2. Does that make sense? This is kind of a boring function. It's a straight line straight across. It does not matter what value your x is. You're getting 2 either way. The answer is always 2. And so this is known as a constant function. So if I want to talk about some properties here, what's the domain of this graph? Anything, I guess. What can you plug in for x? 5, 7, -2? Does it really matter? No. What's the range of the graph? Well, the range of the graph is not anything you want it to be. The range of the graph is literally one number. The range of the graph is y equals c, c being whatever I made that number. So in this graph here, the range of the graph would be y is 2. That is the only number you get. So in terms of this vending machine only gives back 2s. And that's it. You can't get a 3 or a 5. I'll talk about degree in a little bit here, but you guys know even and odd numbers, right? Maybe I should talk about that now. So 0, 2, 4, 6, 8, those are even numbers. 1, 3, 5, 7 are odd numbers. So technically, because this is an x to the 0 type of graph, this is an even graph. There are no x-intercepts. I mean, look, does this graph ever cross right there? With an obvious exception. What happens if the graph was y equals 0? In that case, then everything would be an x-intercept. Because like literally the graph would be going right across the line here. Does that make sense? Okay, so now we're going to bump it up a notch. What happens if rather than being an x to the 0 graph, what if it's now an x to the 1 graph? So like a good example here would be y equals 3x to the 1 plus 4x to the 0. Now, we don't usually write it like that. And that's not even what this graph is. Usually we just write it as y equals 3x plus 4. But do you guys get where I'm going here? Where now it's a degree 1 graph because there is a 1 as the exponent. And you guys learned about linear graphs in grade 10 probably? So this number right here is the slope. This number right here is the y-intercept. So in terms of properties then, this guy, well, you can still have any number you want for x. That doesn't change. In terms of your y values, well, this graph goes for forever in both directions. So you can get any y value you want. Because this number right here, the largest exponent we have is 1, it's now an odd graph. And I guarantee you, you have to have one x-intercept and one y-intercept. I don't care where you put this graph. Like, let me just draw some other random graphs here. Let's say I put it way over there. Look, there's one y-intercept, one x-intercept. There has to be. And you might say, well, what if you put the graph like way up here, like that?
Mr. Forrester, can you please call 100? Mr. Forrester, please call 100.
See how there's a y-intercept for sure, right? Do I see the x-intercept on this graph right now? Well, no, but if I like kept it going for like ever and ever and ever, there eventually would be one. Does that make sense? Shoot, I lost the little change button. Where'd it go? There it is. Okay, so then quadratics, what we learned last year then. So we write them in a couple of different ways. Sometimes we write them like this. This was known as vertex form, if you guys recall that idea. This P and this Q referred to where the vertex of the graph went. That was another way we could write these things. But most of the time we're going to start with standard form. So it might look like this. You might have some x squareds, you might have some x1s, and you might have some x zeros. So like here's a good example. It could be negative 3x squared, 4x, and 7. That being said, I'm going to write it this time here, but like don't write the 1 right there, and don't write the x to the 0. But does that make sense that they're implied? So then for properties. Again, is there any reason why you can't plug in a number for x? Well, no, you can plug in whatever number you want. By the way, for starting out, this is almost always going to be true. Eventually, I'll start showing you some graphs where x can't be certain things. But as a general rule of thumb, at least as we start, it's pretty much always true that x can be an element of the reals. So then here's our range. Y is either greater than or less than a number. And that number depends on that vertex. That Q value depends on where your vertex is. So like as a couple of possibilities here. If your graph looked like this, it would be y is less than, say, negative 2. Or if your graph looked like this, it would be y is greater than 3. That makes sense? Okay, and then what we talked about a lot about last year, you can have one answer for an x-intercept, you can have two answers for x-intercept, or that really weird possibility at first, the answer that there are no x-intercepts. The answer, there is no answer. Does that make sense? Okay, so gone through the first three, so let's talk about extrapolating these to then new functions, like say a cubic function. So in general, if you look at a cubic function, first of all, I have a typo on here. See how this is to the power of 2 and that's the power of 2 still? What should it have been? Yeah, this one should have been a 3. So what should happen on a cubic function then is it should start in a low quadrant like this and end in a high quadrant like this. And what we sometimes start to pick up on is it kind of looks like a linear function. You know how linears were straight lines that go all the way through here? With a twist. Rather than being straight, it often has like a little bit of a curviness to it. Sometimes it has like a complete little flip like this where it completely turns around. But it should always start low and end high. Or there's actually the possibility that it could start high and end low. Any idea how I make the graph go from this to this? That's it, yeah, the negative leading coefficient. You know how a negative leading coefficient turned a graph from this as a quadratic to this as a quadratic? Well, if you have like a positive, kind of doing like a disco move here, from your perspective, this is a positive linear graph. If I make it a negative graph, that's all I'm doing here is I'm going from here to here. Only linear is straight, cubic is more of like a this kind of thing. That's where there's going to be like a little twist in the middle. Where that twist is, how big that twist, totally depends on the graph. I can't give you any hard and fast rules for that. The graph could look kind of like this, where it just kind of flattens out a little bit. It could have like a totally distinct kind of piece to it, but like it's going to have a bit of a twist. And so one of the reasons why we call it an odd degree is it's very similar to the other odd degree graph we just did. Linears and cubics are very similar. Does that make sense? Okay, here's a couple possibilities. I guarantee you there's going to be one x-intercept, but there could be two or there could be three. We don't know how many there will be. And let me just show you some pictures of examples here. Here is a cubic graph with one x-intercept. That makes sense? But here could be a cubic graph with three x-intercepts. And it just kind of depends on how that little twist plays out. Now, you can see how that little twist right here, I made it very, very slight. And it didn't come high enough over the axis to actually create more x-intercepts. But then here, I made the twist very large and exaggerated. That just depends on like the graph. And I can't, like I said, I can't give you any rules that I can say always this makes it work that way. So it just depends on how the graph turns out. You can actually also have two. That one's a little trickier. It has to come up, just barely touch right there, go a little bit below, and then above. And see how you have two x-intercepts then? But I guarantee you have to have one. There's no way you can have zero, because if the graph has to start down here and end up here, it has to cross this line somewhere in there. Okay. So then let's bump up to quartics. Well, quartics are kind of similar to quadratics. You see how this looks like a quadratic, only rather than being like a nice U shape, see how it has like that little twist in the middle there? Kind of the same principle as a cubic. I don't know how much the twist is going to be, how deep it's going to be, but there's going to be some sort of twist in the middle here, and that's the property of a quartic. So it goes to the power of 4. So it's got similar properties to other even graphs. X can still be anything you want, but your y values are really limited based on how low or how high the graph gets. This graph right here has a minimum value here and a minimum value here. Which is the one that's going to determine the range of the graph? Like the lower one. So like this y is greater than -3, it looks like, based on that little bit. Does that work? So quartics then, kind of like quadratics, they can have a whole bunch of numbers of x-intercepts. And we don't really know how many there will be. Let me show you some just examples of what this graph could look like. You know how quadratics, though, they always go like top to top, like this, or bottom to bottom? So that's why I wrote here it starts and then ends in the same hemisphere. So like let's say it starts up here and ends down here. This could be a quartic graph. It looks like a quadratic, but there's that little like bump in the middle. Does it have any x-intercepts? No. You could have a graph that looks like this. Has that little kind of squiggle in the middle there, and it just barely touches once. Make sense? You could have a graph that does this. A really exaggerated, like quadratic looking thing, and then kind of like a little twist right here. And here it goes twice. So hopefully you can kind of imagine all the other possibilities. You could have a 3 graph that looks like this. 1, 2, 3. And you could have, if it was like a really exaggerated W, some some quartics very much look like a W. And you'll have 1, 2, 3, 4 different roots. Does that make sense? Cool. Okay, well once you get these principles, you can keep going higher and higher and higher. Like I could tell you what an x to the 6 graph looks like. An x to the 6 graph will start up high and end up high. If it has a positive, it could be upside down. And then it will have, like, say, 1, 2, maybe a flip, maybe another flip. There's an x to the 6 graph. That makes sense. And I can kind of tell because there's like 1, 2, 3, 4, 5 different kind of turning points. Where those turning points are, how exaggerated they are, I can't tell you that. Like, it really depends on the graph. And one of the reasons why it's too hard to tell is because all that we know is that there's an x to the 6 at this point. But it depends on how big the x to the 5 value is. And it also depends on how big the x to the 4 value is. And what if it was a negative x to the 3 value? All of the rest of this stuff in here also affects the graph too. And there's too many variables now to be able to tell. Does that make sense? Okay. So, last thing here then. I want to try to match these 4 graphs to these 4 equations without actually like typing them in our calculators. I just want to try to figure them out just by knowing properties of graphs. So, for example, right here, what sort of graph does this look like it probably should be? I'd guess probably quadratic, right? I mean, it's an upside down. It doesn't have any extra little twists in it. It's upside down. So this one right here seems like a really good possibility. It's got a negative leading coefficient. It's quadratic. What's the y-intercept based on this equation? 0. What's the y-intercept on this graph? 0. Does that make sense? Let's go down and do this guy right here. This one should hopefully jump out at you. It should be linear, right? And only one of the equations I gave you is actually linear. The fourth one, right? Double check some properties. It's going downhill. How do you get a graph to go downhill? Negative leading coefficient. Where's the y-intercept? Looks like the y-intercept's down here at -7. And look, you got a -7 right there. So that seems to fit. Let's do this guy right here. You see how this guy, I mean, I know the window size is not perfect, but you can hopefully see how it's got that little flip right there. What kind of graph? The third one, yeah, we call that cubic. Positive or leading coefficient? Well, because it goes in a general uphill direction, it should have a positive leading coefficient. So that's why it should be this guy right here. The y-intercept is 8. And it looks like it probably crosses there at about 8, so that seems to fit. This last one's probably the trickiest one to see. It looks like it's quadratic, doesn't it? Here's the problem, though. You might not be able to see without zooming in, but chances are it does like a little flippy thing down there somewhere. And maybe it's so subtle that you don't even notice. So as a general rule of thumb, if it does like this sort of thing, yeah, it's probably like quartic. But it is very possible that based on what you see, it might look quadratic, but it could actually be to the power of 4. So because it's the only one left, this one's going to have to be the one to the power of 4. Okay, that makes sense. Okay, so a quick recap of some of the things that I hope I taught you, or at least reminded you of today. Graphic calculator skills. We're going to need those as we go along. Being able to type things into our calculator, find where the graph is, do things like value, intercept, 0, max and min. Hopefully you get the concept of a function where we're going to put in an x value and find a y value. And depending on the complexity of the function, they're going to start looking funnier now. Like, it used to be straight lines or quadratics. But now we could get a graph that looks something like this. And hopefully you're able to look at this graph and tell me some things and say, this is probably a cubic graph. And I know it's cubic because it goes like 1, 2, 3. Hopefully that kind of would make sense. And you can recognize that with more experience. Our goal over the next couple of days then is we're going to start learning to put these types of graphs together and to learn to solve them algebraically and to work within our graphing calculators. Sound good? Okay, there's really not much to do from this section, to be honest. I have an assignment out. Did you guys all get a copy of it? You can't do any questions on it based on today's information. Tomorrow and Fridays. No, tomorrow is Friday, isn't it? Yeah. Nice. Okay, Friday and Tuesday's information to work on this. So what I would suggest here, if you guys haven't got your textbooks, go grab a textbook from Noni in the library. You got 10 minutes here. These are the pages that I went over. There's not really a lot of questions to do. This is day 1, basically. So, I don't know. You got 10 minutes of free time then. Sound good? I guess what you could do is print off tomorrow's notes. And I'll make a video of